Everybody, welcome back. This is Fluid Mechanics homework number 2. This is part D. And part D is asking us to derive an expression relating the maximum angular velocity at which a cylindrical container of height h, radius r, and filled to a depth d with a fluid of density rho can be spun without the fluid spilling out. So the first thing we're going to do is we're going to derive the expression of the height of the fluid when it's spun. So we know that the fluid when it's spun creates a parabolic shape. And if we're trying to find the pressure right here, we know from a vertical standpoint that pressure equals rho gh. However, if we're trying to find it from the center of our parabola here, we'll have to use P2 is equal to P1 plus rho omega squared over 2 times R1 squared plus R2 squared. P1 in this case is 0 because it's located at the center of the parabola, and R1 is also 0. So we will get P is equal to rho W squared over 2 R squared. And if we compare this pressure to this pressure, because they're equal, we'll get rho GH is equal to rho omega squared R squared over 2. And we will get H being equal to omega squared R squared over 2G. So this is our H. And now let's look at a different diagram here. So we have our cup, and it's filled with water, and it's about to be spun by an angular frequency of omega. And when it's spun by that angular frequency, we can see that this parabola forms. And we're trying to find the height at which the water won't spill out of the container but meets the top. So, trying to find that. And the water has a depth of d and a radius of r, since we're in a circular cup. And what you'll notice is that when it is spun, the center of the fluid actually lowers down. So say that this is our fluid before it's spun, and this is our fluid after. This volume that is up on the sides would be equal to the volume of the fluid when before it moved down to the lowest point. So this point would be here. So these two volumes are the same. So the volume before it was spun, we know, because it is the surface area, which is circular, so pi r squared, times, we'll call this small d for depth. So that's the volume of the fluid before it's spun. And we know that this is equal to it. So how are we going to find the volume of this fluid when it's spun? We're going to be using the Shell's method from calculus. So what that does is, if we're looking at it from above, we're going to take cuts, these cylindrical cuts of differential thickness dr from a radius of r, and we're going to add them all up together. This volume will be equal to the integral from 0 to r of 2 pi r h for the height to get the surface area times dr to get the volume. So now we can replace some of our variables here. We know that h in this case is going to be equal to omega squared r squared over 2g. So we'll plug that in. dr. The 2's cancel, and we get pi omega squared g on the outside of our integral, and then from 0 to r of r cubed dr. And we know the integral of r cubed is just 1/4 r to the 4th, so we'll bring the 4 outside, so we get pi omega squared over 4g of r to the 4th from 0 to big R. So we'll get pi omega squared big R to the 4th over 4g equaling the volume of fluid before it started spinning. So from the lowest point up. So if this was our parabola and it touched the lowest point, this volume. So the next thing we want to do is we want to compare our two volume equations we got. So we got pi r squared times the depth equal to pi omega squared r to the 4th over 4g. These are our two volume equations. So we'll lead us into d minus omega squared r squared over 4g plus omega squared r squared over 2g is equal to big H. And of course in this case big H is equal to the height of our cup. So our angular frequency would be equal to the square root of 4g h minus d over big R.